In the third section of Young and Freedman's University Physics, they expand the understanding of work into situations where the force is not of a constant amount, or where the force isn't going in the same direction. Work, as you recall, is force times distance. So the unit is going to be Newton meters, for example, is the standard. So what is the work when the force is not constant? That is, what if the force varies? Let's start with straight line motion, as Young and Freedman do in 6.3. What if the force is not the same amount, but it's still in a straight line? Well, basically this becomes a integral calculus situation, where you take whatever, and this, by the way, this is all straight line force. This is f of x, the force graphed against the distance, where the force might increase. In this particular graph, the force increases as the distance increases, and so basically, using integral calculus, if you divide up the this curve into units, and of course create a smaller and smaller additions, a summation of the areas under the line, eventually you find that when the force varies in a straight line, the work done is going to be the integral from x1 to x2, whatever the distance is, total of fx dx, the integral of all the infinitesimal forces under that curve. The area of under that curve is going to give you the total work done over that period from x1 to x2. So that's fairly straightforward use of integral calculus to find the total amount of work over a certain distance where the force is of varying amounts in a straight line. Now, what if the force is coming from varying directions? Here we're going to have to do the dot product, which of course ends up being the cosine multiplying by the cosine of phi, in this case, or the angle. And so dl in this situation is the infinitesimal amount tangent to this line. If it's moving from point 1 to point 2 with varying directions, the force is not straight on, but the force is in some way at a skew, then at any one point the force at any one point is going to be the f amount times the cosine of phi here, and of course if you then take the sum of all of those infinitesimal dl's over the course of going from p1 to p2, then you have that the integral is going to be or that the work done over that distance where the force is in varying direction, the integral from p1 to point 1 to point 2 of the vector force dot product with that infinitesimal. Or to put it in the way we mentioned it, and I'm sorry the arrows haven't lined up, the arrows are supposed to be over the f and the dl, that the dot product is going to be the amount of the force times the cosine of phi, that is the angle between the direction of the force, or whatever the resultant of all, it could be many forces, but whatever the resultant of those forces is, times the cosine of the angle between that resultant and the tangent to whatever the movement is at every point, at every infinitesimal dl point. That's going to give you the total work done over that distance. So a little bit more complicated here in this video, but this is an extension of the formula for finding the amount of work done, where work equals force times distance, in situations where the force varies, in which case you're going to do the integral from x1 to x2 of fx dx, or where the direction of the force is not a straight line, and in that case you're going to do the integral from point 1 to point 2 of the force times the cosine of phi at each point, at each infinitesimal dl. And so that is work when the force varies or when the direction varies.